So I have a couple of other fun demonstrations that we didn't see last time. This is an electromagnet. Someone pulled off a little part of the casing right here. So you can see the wires. So this here is a solenoid. A bunch of wires wrapped around. I don't know how many turns there are. This here is an iron core. So when current flows through this solenoid, the solenoid will produce a magnetic field. And because this iron core is in the region where the magnetic field is, its little domains line up and it becomes magnetized as well. And so we get a stronger magnetic field. We get the field of the solenoid adding to the field of the core, and we get a stronger field overall. The other nice thing is this core, because it extends out of the solenoid, it extends the magnetic field up further than it would necessarily go with just the solenoid itself. Now I'm hooking this up to the wall outlet. The wall outlet is a source of alternating current. So the current through this solenoid is going to be changing with time. It changes very quickly because our wall outlet operates at 60 Hertz. That means it flip-flops directions 60 times a second. I have a little aluminum ring. Aluminum is not a ferromagnetic material. I didn't bring a bar magnet, but I cannot pick this up with a bar magnet. You'll just have to accept that since I didn't bring one in with me. Right now the coil is off, but if I turn it on, we get a little reaction there. So we have an induced current, induced voltage in here, because of the changing flux. Here, this is creating a magnetic field. The whole, call it an electromagnet, is creating a magnetic field, and that magnetic field is changing with time because the direction of the current and the magnitude of the current is changing with time. So we have an area. When I have this down here, there's field passing through that area, and since the field is alternating with time, we end up with an alternating flux, which in turn is inducing a voltage and a current. So we can levitate it because of the repulsion there. Interesting thing though, if I take this same coil, a coil that's similar, there's a slight difference. I don't know if you can see it from where you're at. There's a little teeny tiny slit in here. If I put that one on, it won't jump. There is an induced voltage because there's changing flux through this area. But we don't get an induced current. And we don't get an induced current because there's no complete path for the charges to flow through. We have to have a complete path. So that one doesn't do very exciting things. If I take this ring, it doesn't have a break in it at all. If I put it on, it gets repelled as well, but not by as much. Why do you think this one has a weaker repulsion than this one?
Because the area is greater?
A little bit to do with the area, but it's not as much due to this area.
Less electrons?
There's less cross-sectional area, exactly, so that not as many electrons will flow through. So by far this is the funnest one. So the repulsion goes with Lenz's law. With Lenz's law, so let's say we have our coil here. Sorry, it's ugly. I'm trying to draw it kind of as a side view. Before I turn the electromagnet on, there's no flux. There's no field here, so there's no flux through this coil. With induction, you can think of objects as being, not that they really have feelings or anything, but you can think of them as being happy with the state they were just in. Not too keen on change. So initially there's no flux. When I turn the electromagnet on, there's now an external magnetic field. So let's just look at the instant I turn it on. Let's say the magnetic field at that instant is upwards. So initially there was no magnetic field. The instant I turn it on, it's upwards. Now it's going to change, but at that instant, our coil was perfectly happy having no flux. We've now created a flux by turning on the electromagnet. According to Lenz's law, the induced current in our coil is always going to oppose the change in flux. So flux changed. It was 0. It's now not 0. So the flux increased. That means this coil is going to create its own current to try to decrease the flux back to what it was. Try to decrease it back to 0. So this coil is going to induce a current such that its own magnetic field opposes the external magnetic field. So this is the induced magnetic field. In order for this coil to produce a magnetic field inside of it that goes downwards, right hand rule, if I want my fingers to go downwards inside, my thumb needs to point this way. So if I was looking at it this way, my thumb is pointing clockwise. So the current will flow clockwise in this, at least initially. So it induces its own magnetic field opposing the change. So the current induced is clockwise on that coil.
How would you do that using the IJK? I trust J.
Too hard to think about.
Should have spent some time on that. I've only done the IJK so far.
As the flux decreases, because this magnetic field is changing with time. So it gets bigger and bigger and bigger, then it gets weaker and weaker and weaker in the same direction, and then flip-flops directions. As the magnetic field decreases, the coil was happy with what it just had. Okay, it's always happy with what it just had. It doesn't want to change from what it just had. So if it had a magnetic field going upwards, but the magnetic field was getting weaker and weaker and weaker, then it would induce its own magnetic field in the same direction to try to increase it back up. So basically, if your magnetic field is getting bigger, it's going to induce a magnetic field in the opposite direction. If your magnetic field is getting weaker, it will induce a magnetic field in the same direction, which requires current to flow counterclockwise there. That's the essence of Lenz's law, is an opposition to a change in flux.
So that aluminum ring wouldn't do that if you had an AC electromagnet?
Actually, it would do it initially, just as I turned it on, because if it had no current to having current, it would jump initially, but once it was on, if I put it back down, it would just sit down. It wouldn't levitate.
It's all about the change.
Yes. So just initially it would have a change, but then it would stay constant, so nothing would happen.
The reason why it bounces is because their magnetic fields are opposite of each other, so they repel each other.
It's actually repelling half the time and attracting half the time. As the magnetic field is getting bigger, the magnetic field is in the opposite direction. If this external magnetic field is getting smaller, the magnetic field is in the same direction.
So if you were able to suspend it horizontally, would it kind of just oscillate back and forth?
It still would have an overall net force away. So we need gravity to hold it down, to levitate it. Another fun one, going along the same lines. This is a copper tube. It's a solid copper. Nice and circular, long. Copper is not a ferromagnetic material. I cannot attract copper with a bar magnet. I have two different masses. They used to look the same, but they don't anymore. One of them This one right here, still sort of shiny on the side, still has those rubber ends. This is just a normal piece of metal. This is a ferromagnetic material though, because it's attracted to my magnet. I don't know exactly what it's made of. This is a magnet. It used to have the same covering and the same rubber ends, but over time that has disappeared. It's falling apart. But it's still fun. So I take my regular mass and I drop it down the tube. Gravity accelerates at 9.8. Maybe a tiny bit less if it rubs against the edges, so a little bit of friction. But if I take my magnet, it takes a lot longer. And it doesn't matter which end I put through first. It's still going to take a lot longer. Okay?
You need a transparent limit too, so
That would be cool.
Yeah. Yes.
That would be cool. Reason why? Same reason here. There's an area. Right now there's no flux through any part of this area. But the magnet, when the magnet's coming down, it's changing the flux through that section of the coil, of the tube. Well, if the magnetic field is if the flux is increasing, so if you imagine the magnet right here and look at a piece right underneath it, as the magnet falls towards it, the flux is going to increase because the magnetic field is stronger closer to the magnet. As the flux increases, there's actually a little current induced in the wall of the coil to create its own magnetic field in the opposite direction to try to oppose that increase of flux. Now let's say it was completely successful. Let's say enough current flowed to cancel out the magnetic field of this incoming magnet. What would happen? If it could cancel it completely, it would stop it. But if this magnet stopped, what would happen to the current induced in the walls of this tube? It would stop. Because the flux wouldn't be changing anymore. If this stopped and was stationary, the flux wouldn't be changing. Which means there can no longer be induced current. If there's no induced current, then there's nothing to oppose this moving. So it falls. So basically, the current is always induced, is always trying to oppose the change in flux, but it can never be permanently successful in doing it. The flux, it ends up slowing down the magnet, but it cannot stop it because the induced current would go away and we would not have current anymore and no opposition to the magnet. So, fun examples. We're going to look at a couple applications, a couple of more applications of Faraday's Law. We're going to look at generators and transformers. And then we're going to look at a circuit element called an inductor, which is basically a little solenoid in your circuits. So we'll look at circuits with inductors and resistors, with inductors and capacitors, and we'll start doing that tomorrow.